связаны с глубинным
We will wait maybe 2 minutes.
Okay.
Because we wait the Ilya from press hall.
Yes.
Это все могут это все за. Значит, я на эту тему тебе ничего не знаю. Это отдельно очень тяжелая проблема. Я боюсь, что я и многих моделей.
Мы буквально 2 минуточки ждем, сейчас должны подойти из прессового зала. Евгений Александрович,
вот эти данные,
все, мы дождались. У нас сегодня не совсем запланированное такое заседание семинара. Today we will listen to the report of Professor GUO from GUO about his laboratory geomechanical experiment on the K laboratory of earthquake administration of China. And this visit to Moscow, Professor GUO, in framework our collaboration by RFI Foundation. And I think it will be interesting report because Professor GUO a lot of time research problem of destruction rock on the not only small samples but large samples, such centimeters. That it is maybe very interesting. Please, Professor.
Okay, thank you. Thank you, Professor Fiziki. Thank you for your invitation for us to my first trip to Moscow and IP.
Microphone.
Андрей. Бежал? Нет, выше.
Oh, thank you. This is my first travel to Moscow and IPE. I remember Fiziki came to our laboratory maybe 2008. Yes, and then we did some cooperation projects in indoors and field work. Now, today we introduction give you about our laboratory first, and then we talk about our big project about both metal instability states. Let's begin. This is my institute building. Only one, but maybe next year we get another one for 2 laboratories. part one, I introduced the upgrade of technologies testing equipment. It's repaired our machine from 20 tons. Last about several years, and we updated our price and observation system, so it is fit to our scientific purpose. And sorry. Oh. Yes, a brief history of Institute of Geology. After, because we changed our name about 4 times, and since 1971, the setup. But at that time, we listening with the Chinese academic of science. But after that, we changed to controlled by State Seismology Bureau. After that, and we another renaming again since 1998. But now we change China earthquake administration. It's a joke. Is maybe in China we can control earthquake, so we change the name administration for manage. Okay. Our laboratory is belongs to a state key laboratory of China about the earthquake dynamics, established in 2003. It's an academic margin. He's the first laboratory academic committee chairman. It's first. She studied in IPA as about 4 years from 1958 to 1962. Our key laboratory has 6 divisions. This hour is I work with this laboratory, technologies laboratory, and others the other 4. Till now, the two divisions added our key laboratory. Yes. For our key laboratory, we focused the scientific aims about earthquake dynamics and strong earthquake prediction. That's our task for a long time. We have some task input some data from the distribution feature of tectonic deformation, just like as inside the leader. And another group do some work given environment of tectonic deformation and the seismic area and the electromagnetic areas data. And this is for to study the tectonic deformation evolution history and the aging. This is our group. Is the physical mechanics of tectonic deformation. Is including the physical experiment. Later we will introduce about this, and some numerical simulation is another group to do this work. And for us, we get the task from government. This seismic evolution change and risk evolution. It's just like Professor Dubetsky did work about this. And we also observe some seismic precursors in field and indoor. Finally, we can investigate earthquake mechanism. Yeah. This our laboratory, tectonic physics. We have 4 parts. Is high temperature, high pressure recommended analysis. It's controlled by Professor He, and high temperature and pressure local physics is by Professor Yang and Zhou. And this I work this sub laboratory is technical-based deformation and physical field is the Professor Liu, Ma, and another one is for low to high speed fraction machine. It's by Professor Ma, but he isn't in this picture. It's made by Tokyo or Professor Toshi.
This picture made
maybe 5 years ago. Yeah, but I can't find the new one. Our have so many international cooperation projects and other cooperative research. That's like Russian academicians, Sherman and Barnicoff and Rubetsky, and the U.S. Lochner and Lapista and others, and Japan and that's the Tosi, and the Netherlands and Chris Spass professor, and German and other Canadian professors. Also, we can do some work together. Oh, now we introduce some price in our laboratory. First one is made by Professor He. It's a high temperature, high pressure machine. It's with gas media, and later another with a solid media for convenient price. Pressure. This is inside. It's here, the chamber here. This machine can complete the temperature for sample about to 600 degrees. Yes, 600, and vertical load up to 3 gigapascal. And the convenient pressure is 400, about 400 megapascal. Its power pressure is 200 megapascal. The loading rate is from this to this. So we can use the machine to measure stress of fault fracture and the loading rate. This low loading rate. Okay. This machine can simulate out from here to here, from the surface to the 50 kilometers in depth. Okay. And the next one is for marine rock physics and grip parameters. This is a super high pressure for 2 gigapascal, and the temperature is more higher to 120 or 200 degrees. And another one is just I mentioned. With this machine, the convention pressure is with solid medias. And another one, this one is gas, with gas for convenient pressure. Yes, it's a different type. Use these two prices, we can measure velocity in different temperature and convenient pressure and we can also measure the rock conductivity and others plastic parameters and for grief parameters. Yeah, they also can get some parameter from the surface to about these 50 kilometers in depth. This a young guy made it about 7 years ago. This named fluid flow testing machine. We can measure the permeability, including from this value to this value with a different media and different method. So we can measure all the cases of parameter for this for permeability. After testing, we also can observe some information from the sample. After that, we can to observe the microscope composition for the rock samples and other samples. We can do this. For example, the XRD and the SAM and the EBSD and FIRD. So before testing, we can detailedly to prepare our sample. After the price, we can also get some information from the sample through many apparatus. Yes, I worked at these several laboratories. The first one price is for Bell axles. We can this one price 2 directions. This one up to 150 tons. We can control this machine by IVT and by low shell. We can accomplish by synchronous and servo control. We can yes. This part is for synchronous control loading, and this part is for asynchronous thermal control. So we can do some experiments with ionic control types. This universal testing price for tension and compression load. So we can this about tension load. Another this part for compression load is we only use this price to get some parameters of rocks, just like Young's modulus and Poisson ratio and others, cohesion and fraction angle. And the third one is the low high speed fraction machine is made by Japan professor Toshi. We can use the machine to simulate the co-seismic slip of fault. The rate about from this very low rate to the high rate. I remember it's about it's equals to for 2 meters per second. This value. And we also do some with the convection pressure experiments from 1 to 35 megapascal for convection pressure. Oh, the 2 machine is ongoing to make. Maybe next year we can get the machine from factory, and this one is under repairing. I think maybe at the end of end of this year we can get this parameter maximum unload 1,000 tons and a compressor with 500 megapascal and the power pressure about 160 megapascal. But this parameter maybe next year we can get the chamber another for the heating and the sample inside chamber. We can get these parameters. And for this chamber, we can put 48 plugs for the gauges. We can transfer the signal from this chamber and connect our observation systems. Later I show you. And this new machine, I designed it maybe 3 years ago. Maybe next year we can get this machine from the factory. I changed the general design type. I put the 4 pistons around the frame. Yes, so we get the symmetrical stiffness for sample. So for before the sample 2 sides, the stiffness is the same. So it's different the universal loading price. This machine can load sample size about 1 meter, and with chamber we can get about 0.3 meters inside. We can also increase the convection pressure for sigma 3 up to 50 megapascal in this chamber. Oh, this our observation system for big sample in our laboratory. For example, we can measure the points about up to 128 channels for one sample. We can also measure strain and temperature, for sleep, and velocity, and other parameters for one sample. We also observe with the camera. The high-speed camera is a high-resolution camera, and the thermal infrared camera to observe the surface deformation and temperature change. This for our 4 groups observation system for our sample. For example, this for strain about 10. But another system we can record the data with 4 megahertz, but only 64 channels. And we also have two kinds of AE system. One system is 32 channels for continuous record of AE full waveform. But if we change the channels to 8 channels, we can increase the sample rate to 10 megahertz. And another AE system is triggered record for AE waveform. It made by Professor Liu Liqiang. He also visited here about 2008, maybe, I remember. And another system for measure the temperature is up to 96 channels. This is resolution about 2 megahertz. Based of so many machines, we can get some investigation. But now we all focus some mechanism of laboratory earthquakes and physical field during lump sample deformation. This is our primary task. And this the Professor Liu Peijun and composed 2 software to research laboratory seismology from a technique. Later I show you some results. And the Professor Ma Shengli and Yao Lu, and to focus mechanism for the low high speed fraction. It's for the keys of seismic period. The last two directions is to monitoring on remote ground temperature. It is controlled by Professor Chen. Is do this work, and another one is monitoring of high frequency earthquake. Is controlled by Professor Yang and Professor Liu. Another Liu. This is some result and some method in our laboratory. This is to simulate the bending fault. About this fault, this is the angle about 5 degrees. Yes, 5 degrees. Yes. We analyze the data by our software, stream tensor analysis software is developed by Professor Liu and I. This is another middle frequency sample rate system of the data. We find during the before the fault instability, we can get some new information. It's not like this only drop like this type, but it's changed with the higher frequency sampling. We can get some new information. It's this stage can be divided into 3. It's part 1 is decrease, and then we get the wave. And after that, we can get a low frequency wave. This is a high frequency wave. So that's why we update our observation system and update our price machine to observe the new information before the fault instability and rock and before the rock fracture. This another method is digital image correlation method. In our laboratory, and Dr. G and Zhuo can develop the new software GUO Yanshuang to analyze the deformation with digital image from the high-speed camera and the high resolution camera, just I mentioned in the last picture. And I also bought a new software from the company. It's VNC2D. We can also to analyze the deformation from of the sample surface. Oh, sorry. Oh, this is a sample for Brazil test with the AE system of the wheel. We can get the 3D location with this new software. Is developed by Professor Liu. And we also get the thrust faults, the micro rupture along the fault strike. We also get the result from this software. But till now, the Professor Liu composed a new one for the AE-scan 3D. AE-scan analyze the sample with the different layers, different materials. But for this software, only analyze the homogeneity materials. So that's different software. This is well, we also get the moment tensor of AZ from this software, and get the 3D location for the surface crack propagation. Maybe this result of testing maybe 10 years ago we got it. And and this picture shows us the temperature evolution of faulting faults. We pasted about 49 PT sensors along this area. We will find the loading. The first stage when loading the sample is the temperature of sample increase with loading, and when the fault sleep, the temperature of a long fault is increased so fast, but the level is so small. This result obtained by Professor Chen. We can load the sample with two directions, at the same time. But another situation is one is the compression and another one is expansion. So for this case, we can get the volume price change only. This one, but for this one, it's only the shearing deformation happened in this sample. We observe the temperature from the surface of sample. We can get when we load its increase and the temperature also increase at the same time. But another case, the temperature may be keep the stable and time. So we get some information about this situations for electric field, and the temperature increase with volumetric stress, not shearing stress. And the two pictures came from the thermal infrared camera. It shows the same situation for these results. And this observation for fieldwork is set up by Professor Chen. He put some sensors along the Xianshui fault, and some temperature sensors in the hole, the different types. For example, about 10. This is about 5 years ago. The hole is very shallow, but until now, the drilling hole, it can maybe I remember about 100 meters in depth. They get some information from this temperature area. This is another field work by Professor Liu. We can get some parameters. It's 8 channels for this machine, and we can set different gain in this controller. We also can get the frequency of about 5 Hz to 1000 Hz of this. We can get the data of high frequency macroseismic station. We also put this system outside maybe 5 years. 5 years ago, we set an over. The part one, I show you some price machine and some observation systems indoors and outside, and we also show some method in our laboratory. We want use this price machines and analyze methods to get our aim for fault meta-instability stage research. Now I give you some experimental progresses about our investigation for the meta-instability. First one, I show you the physical business for this idea. This is a theory. The fault metal substability is proposed by accretion margin in 2012. They divided the progress of stress strain curves to four parts, and before the peak stress, we can change it to two segments, and for stable and metastable, this is some. This stage we can measure some macro fractures happened in sample, and after the peak stress, and from O to A, it is defined by metal instability, but before the faster sliding along the fault. So we focus this stage to predict the time of the fault instability. This duration is very short in indoors study. Later I show you some the duration time of this one. Oh, sorry. We use some of our machines to observe during the sample load increase, and change the position. We can observe the process loading and loading increase and loading drop off. In this, in many experiments, we obtained the metal instability exists almost in all the state sleep event. It's just like the earthquake happened indoor. This result is published in Chinese journal, but we translate into English. This is cooperative with academic Sherman. This is another. Sorry. We can. This picture shows during the fault sleep before the fault sleep, and during sleep we can show the different deformation along the fault. From this instability start here, but before we can the deformation along the fault is various. It's different. This is another result from thermal infrared camera images. We also get the same result when the loading increase, the temperature rise with the loading, and during the metal instability, the local fault fraction sliding can show some temperature change, and during the sliding of the whole fault, the temperature is increase very fast, but the third temperature is not. Oh, yes. This one. Oh. This result is observation from the high-speed camera. It's analyzed by GUO. We can get the metastability stage before the fault sliding. This result, we can get the three kinds of initial phases of AE signals before the fault sliding. The first one is slow sleep. This means before this, it means the fault are sliding, the whole fault sliding. But before that, this is the signals change very slowly. So it means the slow sleep from here to here. Not so high frequency, very low. And another kind of signals is for just like tremor as a natural. It is just like the natural earthquake happened subduction zones. Yes, there's the several tremors like this, like this, like this, like this, like this, like this. I remember before winter earthquake, some of the station data can also show the tremor. But the duration about a few milliseconds. And the third one is fault shock. It's a very small shock, and just like this, very small. So we next task we can get the difference in different cases. For example, this is slowly sleep is for the small fault, and this tremor is for the fault with the gold, and the fault shock maybe with asperity fracture. So the last part we want to introduce some of our big project in China. This project is ongoing project. It's about a new attempt to explore earthquake precursors. Why we apply this project? There's a background is about this. In 2005, the Journal of Science published 125 problem in 21st centuries. This problem is listed by the 55. So after that, academic margin proposed the study of the earthquake precursor is destined to go from the laboratory to field, because before that, most of researchers do some research investigation indoor, and another part do some investigation outdoor, not a collection with each other. So we update our machine, and indoors machine and outdoors machine. We want to connect with the two parts for to explore the speaker precursor. Our new project, the title is this one: experimental, theoretical, and field study for field work on the identification of faults of the instability stage. This the theory proposed by academic margin 20 and 11. Our scientific aim is two parts. Is to explore the identified marks and characters of faults instability stage of faults from the laboratory to field work. We want to connect the data and the characteristic of fault instability. And another aim is to provide a new seismic prediction method with this theory. Yes, with this theory and this model. Yes, this research division about more than 3 years, but I think it is not enough time for us. But this project started from 2012, funded by NSFC and our institute and the King laboratory. So we have to take more time to investigate this project. Maybe after that we continue on another project to do this scientific aim. Next, I show you some the field work plan in our project. This is for seismic station. We want to set the 2 nights in field work. The one is in Western Yunnan seismic site is located southwest of China. Right here, we want to put up set up the 30 stations. It's controlled by Professor Wang. This is this study, and another high frequency seismology of 20 stations is controlled by Professor Liu. And we also set this site and this the northwest of China, Gansu province. The wideband seismography about 10, and another is the same machine is about 55, a new one. This this one. This is for temperature and GPS stations. The site is the same. The last picture. We set the continuous GPS about 25 stations and the general GPS for 7 stations, and the for temperature observation about 4 stations, and this for on northwest of China. We can get the data from the 33 GPS and the 10 stations of land temperature. This is the field work. This we also set a group to restudy the data of the earthquake cases around our region, our areas in our projects. In this project, we also investigated about more than 300 earthquake cases, and this list of some cases. And some data in previous in study, we get some about nearly 5,000 abnormal information from this earthquake events, including the seismology and the deformation, gravity, and water, and electromagnet. Yes. So we also want to get some new information from these cases based on the theory of fault matter instability. Oh, that's all. Thank you for your attention. This also is only a brief introduction about our laboratory, our focus, and our project.
Какие-то вопросы наверняка есть в сравнении с нашими экспериментальными методами?
У вас в основном речь идет об энергии, но согласно закону Стефана Больцмана, это в экспериментах надо показывать изменения не температурных полей, а изменения в джоулях. Тогда не будет путаницы. Но я говорю о полях, они представлены температурно, они некорректно.
Question about energy and temperature relation.
Какие температуры?
What is the relation between energy inside rocks?
Rocks.
Because you detect temperature only.
Yeah.
It's not energy.
Yeah. I remember the energy for one instability event about it's just like minor 3 to minor 4 magnitude of earthquake. Yeah, for a big sample. Yeah.
It's not energy of earthquake.
Yeah.
It's energy inside common energy inside some
Как берег.
Did you observe the melting during the rock fixing experiment in your laboratory? Melting.
Melting in big sample, we cannot get the melting piece. But for another is friction machine.
Yeah.
Friction machine is get the melting.
Yeah. And you found.
Yeah.
I have also a question about this slide. Your accuracy of measurements is up to 1/1000th of the part of Celsius degrees.
Yeah.
How do you measure so precise temperature?
This would we use the center 50,000, the center. PT 1/3. I show you. Oh, this one. This sensor.
Is it platinum thermocouple?
What?
Platinum thermocouple?
Carbon? Yeah.
Oh, it's,
We will pixel the surface of the sample.
so you have so much, 49 is number of sensors, yes?
Yeah.
Platinum is this is thermocouple.
Yeah.
So if you use 49 thermocouples on the surface of your sensor, of your sample, and you glue it there.
Yeah.
And you think, and it gives you a accuracy of, you think it's give you accuracy of 1,000th part of Celsius degrees.
I'm sorry.
So it gives you accuracy, you think, you suppose, that this sensors gives you accuracy of measurement up to so precise as 1 divided to 1,000 part of Celsius degree.
That's about
Because in my experience, when I measure something, the best that I can make is 1/10 of Celsius degrees or 100, but for thousands is like.
this sensor we can measure about 0 to 100 degrees the range of this one. And the camera for infrared camera is also ranges from this part from 0 degree to 100 degree. If we want to measure the higher temperature, we must make calculation. We do some calculation for higher temperature. Yeah.
Thank you.
Bye.
Maybe before slide, I don't know, maybe where right the metastable.
Oh, the theory.
Maybe
Oh, no.
Whereas the metastable,
Oh, this one, yeah.
what's your opinion about term meter, only meter?
Yeah.
Maybe on this figures we can write stable and unstable only.
Oh, yeah.
What it means meter?
This match with the energy. We can decide with energy. When we loading sample, we can get the strength curve when we decided by the peak strength. Yes. Before that, we covered the stable and imaginary.
Stable,
Yes, stable. Yes, okay. This most of engineering research is focused this part. But for earthquake research, we must focus this stage after the peak strength because the stable stage maybe last 1,000 of years and hundreds of years. But in my opinion, this the incident stage maybe only 1 year or 3 or few years and a few months, even several days. Yes. So we focus this one. Yeah. Yes.
Есть еще вопросы? Поблагодарим нашего
напряжениях, вот, получаемых сейсмологических данных, о техничности, динамике течения провинции. Тоже 10-30 будет, если кому-то интересно, приходите. Может быть, фото, да? Вполне.
Прошу записаться, пожалуйста.
Я Владимир.